So I'm Lapassawansi Warapat. So today I'm going to present about the lab 1, cruise control. So this will be the learning goals for our labs. So first one will be compare and contrast open loop and feedback control. Implement a simple open loop control in Simulink. Analyze the performance of an open loop controller. Implement an app proportion controller in Simulink and analyze the performance of a proportional controller. So in this lab will be separated into two parts. So the part one will be the open loop control and the second one will be the feedback control. So first we will start is the definition of cruise control. So this is the cruise control definitions and also the goal. So the control strategy. So the first one will be an open loop control. So the open loop control will begin with the set point and then connect with the controller, and then we have the input, and then we have the plant will be the symbol like this, and the line will be the speed. So the speed is referred as output. And the second one will be the feedback control. So the feedback will be the same as the top one, as I show over here, but the difference is they will consist the feedback like this and also add with a sum block. So the first part will be start with the open loop control. So this will be the Simulink diagram for open loop control. So the task one, so we have to open the virtual vehicle model. So on the left side will be the virtual vehicle models. So we follow the instruction and then we run out the Simulink. And for the task 2, the question is asked about set the controller gain to 100 and does the vehicle reach the set point of 50 meters per hour. So let me run the Simulink first and we will see the result. So we have set the controller gain to be 100, then we run. So after we run, we can see the result by opening the scope. So we have seen that the vehicle does not reach the 50 miles per hour. It's like around 37, something like this. So the answer will be no. So we continue to do task 3. So we have to identify the value of controller gain to reach a top speed of 50 miles per hour. So this one we will assume to be 145. Then we run out. Then we will see the result that it can reach a top speed of 50 miles per hour by adjusting the gain controller to be 145. So that's fine. So for the task 4, we have to find the top speed. So we have to change the set point to be 70. Then we run out. And we also use the gain controller gain value from the task 3, so it will be the same. So we run. So we can see that the top speed will be around 63. And for the task 5, we change the set point. And then we by the final speed. So we have to round to nearest mile per hour. So it's around like 57.09. So we can see by using the cursor measurement to make it more accurate. So it will be like 57.09, the same. So the B, 5B, so we will change to 70%, and then we run. And then we will absorb the result. It will be around 63.11. So it's the same. Then we, based on our observation, so is the plan linear? So it yes, because at the beginning it come with the linear line. And then the task 7. So we have to double click this one and change from what the instruction said. Be 50. Change top speed to 50 as well. And then we run out. And what will the vehicles go? Also, we have to change to hills as well. And then we run. And we will see the minimum speed reached while driving up the hill. So it will be 17.38. So over here. So next we'll begin with the part 2 for the feedback control. So this will be the diagram for the feedback control. And for the task 9, we have to use Simulink to create the Simulink model diagram to become like this. So this will be the same. And I have following these instructions. So it's the concern with 52 gain blocks. So the first one will be the KP. The second one will be made per sec to made per hour. So we set the follow value to be 2.2 something and then the scope. And then we have to adjust the vehicle image to become 14,800 and okay, okay, fine. Then we set up the KP to be 1. Then we run the scope. we can see that the car is moving really slow. And then we have to look for the value maximum speed by clicking on the scope. So we can see that the maximum speed would be 4.4. So I would change to 0.441. 0.441. So this will be the same as this one. So next we change the KP to be 5,000. So we have to change over here 5,000 and then we run. And don't forget that we have to round to the nearest 100 for both of the. So we can say that when we increase the KP or the gain, the speed of car also faster or increase. So we look for the maximum speed. So the maximum speed will be 48.6 in meter per hour. So the same maximum speed. So the question asks about, does the feedback controller work across a broad range of request speed if we try different set point with the gain value? So we will might change to example would be 20 set point. Then we run. So the answer might be yes. Yeah. So it's the same even we just change the set point. So I answer it yes. So I'll notice that the KPV 5,000, the system still doesn't exactly reach the set point. So we connect a scope to the output of the gain block and also reset to 50. And then we run. So if we make it correct, so the output will be the same as the pictures. So let's see. Oh, right, it's the same graph. So I think it's correct. And then we answer the question over here. On task 13, it say that what is the steady state value of control signal? So it said 6.942 times 10 plus 3. So the answer will be 6,942. Okay, we just round it up to make it this value. Okay, then we continue do this one. We try to find the maximum speed when it reach while driving up to hills. So we change to 50s and then adjust this turbine type to be hill, and then we okay, and then we run. So we can see that the speed is quite fast. So we look at the scope. So the value will be the maximum speed will be around 4.999. Yes, 4.99. So this will be answer 4.99. So the last question will be, does the proportion control be perform better or worse than the open loop control while vehicle driving to hills? So I think it's faster because it takes less times. So it's better than the open loop control. Okay, finish for the lab one. Thank you.